So how do we know if we have to figure out a limiting reactant in the first place? Well, if we're only given information about one reactant or product in a reaction, then we don't have to worry about going through these steps. But anytime that we're given starting information about more than one reactant, we have to figure out which one is limiting, which one runs out first. We can accomplish that by making sure we have a balanced reaction, converting given starting quantities of our reactants to respective mole quantities if needed, figuring out a limiting reactant ratio by taking the number of moles of reactant of each type, divide by its respective coefficient from our balanced equation. We can then use the starting amount of the limiting reactant and the limiting reactant alone to convert to moles of any other component of our reaction. And again, we can only convert moles of one thing to moles of another from a balanced reaction. A flow chart might look like this. We can convert from a mass of limiting reactant, if given one, to moles of a limiting reactant using a molar mass. From moles of our limiting reactant into moles of, say, a product. And, if needed, from moles of a product into mass of a product. Let's do a specific example and determine a theoretical yield. So as an example, let's imagine reacting 50.6 grams worth of magnesium hydroxide with 45 grams worth of hydrochloric acid to produce magnesium chloride and water. What mass of magnesium chloride is expected from this reaction? Because we're given information about two reactants, magnesium hydroxide mass and hydrochloric acid mass, this should signify to us that we're working with a limiting reactant type problem. We're going to need a balanced chemical equation first off. So we react magnesium hydroxide. Magnesium hydroxide has the chemical formula that includes magnesium with a 2+ charge, hydroxide with a 1- charge, MgOH2. Hydrochloric acid is HCl. This reaction produces magnesium chloride, MgCl2, and water. To balance this equation, let's make sure that we have the same number of every atom of each type on both sides of our reaction arrow. We only have one chlorine on the left. We need 2 chlorines, though, to balance with the right-hand side. So I'll put a coefficient of 2 right here. This gives us a total of 1, 2, 3, 4 H's. We only have 2 H's on the right-hand side. So I'll use a coefficient of 2 over on the right-hand side. What I would like to know about is which one of these two reactants will run out first. Which one is limiting? We're given starting masses of these things, so we're going to have to convert these to moles. To do so, we need the molar masses of both of these substances, magnesium hydroxide and hydrochloric acid. The molar mass, or molecular weight, for magnesium hydroxide is equal to 58.32 grams per mole. The molar mass, or molecular weight, for hydrochloric acid is not affected at all by any coefficient that comes up before it. There's just one hydrogen and one chlorine in the formula, 36.46 grams per mole. To convert our starting masses into moles, we need to take 50.6 grams worth of magnesium hydroxide, divide by its molar mass, 58.32. We end up with 0.868. Take this one step further and calculate a limiting reactant ratio. The limiting reactant ratio is the number of moles of magnesium hydroxide, 0.868, divided by magnesium hydroxide's stoichiometric coefficient, 1. Now, do something similar for hydrochloric acid. Convert 45 grams worth of HCl into moles of HCl. Divide by its molar mass, 36.46 grams per mole. We get 1.23. And if we weren't careful, we might incorrectly assume that magnesium hydroxide runs out first. There are fewer moles of magnesium hydroxide, right? But the problem is that for every 1 mole worth of magnesium hydroxide that reacts to make products, 2 moles of hydrochloric acid are required to react. The limiting reactant ratio for hydrochloric acid is the number of moles of HCl, 1.23, divided by its stoichiometric coefficient of 2, which results in a ratio of 0.617. Relatively speaking, hydrochloric acid is actually present in a smaller amount because we require twice as much HCl as we do MgOH2 every time this reaction produces products. Hydrochloric acid is our limiting reactant. It's the thing that runs out first because it's present in the smaller mole quantity. That means that we can completely ignore magnesium hydroxide for the rest of this problem. All we worry about is hydrochloric acid. So I can get rid of this entirely. In fact, now that I know that hydrochloric acid is my limiting reactant, I'm just going to go back to the drawing board and start with information about it. I'm going to convert mass of my limiting reactant, hydrochloric acid, into moles of hydrochloric acid. From there, moles of hydrochloric acid to moles of MgCl2, and then finally from moles of MgCl2 into a mass of MgCl2, because I am indeed asked what mass of magnesium chloride is produced. So let me get rid of the answer here and start tacking on some more conversion factors. To go from what's moles of hydrochloric acid at this point into moles of magnesium chloride, we take advantage of our chemical reaction. Moles of HCl convert to moles of MgCl2 by using coefficients from the reaction above. Coefficient in front of MgCl2 is 1, in front of HCl is 2. Finally, to go from what's now moles of MgCl2 into mass of MgCl2, we need the molar mass of it, which works out to be 95.21 grams per mole. As we move through this calculation, we'll get rid of grams of HCl, moles of HCl, moles of MgCl2, and be left with grams of magnesium chloride at the end. We'll keep 3 significant digits to 3 sig figs. The result should be 58.8 grams worth of magnesium chloride produced as a predicted amount or theoretical yield in this reaction. The sticking point here is that unless we're careful, we could have overlooked that hydrochloric acid was our limiting reactant. We need to take care to make sure that we have a balanced chemical reaction, that we convert quantities of starting materials into moles if they're not explicitly already in moles. And then from starting moles of reactants, calculate a limiting reactant ratio. That's the relative amount of moles, or the ratio of number of moles of reactant to reactant coefficient. Once we have a limiting reactant, we use it and only it to predict the outcome of this reaction. So let's work a few more examples together. Again, I'd encourage you to try these before you watch the solutions to see if you can come up with the right answers. Suppose that we react nitrogen with 3 hydrogen molecules to make 2 ammonia NH3 molecules. If we start this reaction initially with 0.5 moles worth of nitrogen and 0.5 moles worth of hydrogen, which one will run out first? Which is the limiting reactant? And based upon that result, what's the maximum number of moles of ammonia that could be produced from this reaction? Well, here we're given moles explicitly and a balanced reaction too. we can figure out the limiting reactant ratios for our reactants directly. For nitrogen, the limiting reactant ratio takes the number of moles of it, 0.5 moles, divides by its stoichiometric coefficient, 1, a limiting reactant ratio of 0.5. For hydrogen, the limiting reactant ratio takes the starting number of moles of it, again 0.5, divides by its stoichiometric coefficient, 3, for a ratio of 0.17. Therefore, because hydrogen is present in the smaller relative amount, it must run out first. It's our limiting reactant. So, hydrogen is limiting. We can convert from moles of hydrogen into moles of anything else we're interested in the chemical reaction and ignore nitrogen's contribution entirely. So, let's go from moles of hydrogen into the thing that we're interested in, which we can do directly in just one step. That's moles of our product ammonia, NH3. Our moles of hydrogen to start are 0.5. We're going to convert to moles of ammonia by filling in a conversion factor with stoichiometric coefficients. Coefficient in front of ammonia is 2. In front of hydrogen is 3. The result of this calculation, keeping just one significant digit, is 0.3 moles worth of ammonia. So, in a second example, let's react C2H4 ethylene with oxygen to form carbon dioxide and water, another combustion reaction. Suppose that we start this time with 5 grams worth of ethylene, C2H4, and 15 grams worth of oxygen. What's the limiting reactant in this case? And now, what is the maximum mass or theoretical yield of water that could be produced from this reaction? Here we're given a balanced reaction directly, but we are going to have to figure out moles of C2H4 and of O2 from the masses given. Therefore, we're going to need molar masses for both. The molar mass or molecular weight of C2H4 comes from 2 carbons and 4 hydrogens, a value of 28.05 grams per mole. The molar mass of oxygen comes from just 2 oxygens, 32 grams per mole. We need that information to convert given masses into moles. For ethylene, C2H4, our given starting mass is 5 grams. Convert to moles by dividing by the molar mass. We get 0.18 moles worth of it. The limiting reactant ratio is the number of moles, 0.18, divided by the stoichiometric coefficient, 1. Just 0.18 for ethylene. Similarly, for oxygen, O2, we can convert mass, 15 grams given, into number of moles by dividing by its molar mass. This gives us 0.469 moles of O2. For oxygen, the limiting reactant ratio is that number of moles, 0.469, divided by its coefficient, 3. This value is 0.156. From this mathematical workup, it's clear that oxygen is present in the smaller relative amount compared to ethylene. Oxygen runs out first, therefore it is our limiting reactant. So I'm going to start it in the reaction up above. And I don't care any longer about ethylene's quantity because it is an excess reactant. All I need to do at this point is convert my starting quantity of oxygen into mass of water. So we have a means by which to convert mass of O2 into moles of O2. The next thing I need to do is convert moles of O2 into moles of the thing that I'm interested in, water. And finally, moles of water into mass of water. Because we'll need a molar mass or molecular weight for H2O, let's determine that up above. That molar mass comes from 2 hydrogens and 1 oxygen, 18.02 grams per mole. Now we can fill in our incomplete conversion factors below. Our last one, rightmost, uses the molar mass of water. Our central conversion factor that converts moles of O2 to moles of H2O is completed by filling in coefficients. The coefficient in front of H2O is 2. The coefficient in front of O2 is 3 in our balanced equation. Taking care of units, we'll see that grams of O2 go away, as do moles of O2 and moles of H2O. We'll be left with grams of H2O as requested, and as we multiply or divide through and keep 3 significant figures at the end, we should wind up with 5.63 grams worth of H2O.